Now, the last section I want to cover on functional group interconversions involves reactions at an acyl carbon. That's the highest oxidation state. That's the oxidation state for things like carboxylic acids, esters, amides, acid chlorides, things like that. And you should remember this from Chem 342, that this usually goes via acyl substitution. And acyl substitution is not like SN2, where you just get a thing coming in and the leaving group leaves all in one step. It involves addition to form this tetrahedral intermediate, followed by nucleophile elimination. So let's go through this in a little more detail. The example I've shown is for an ester and an amine reacting to form an amide. And an alcohol. So the amine comes in and in effect displaces the alcohol. That's the substitution that's going on. This example is one that I've taken from my own personal experience. This was never published, but it's a reaction I ran many years ago. So the nucleophile addition occurs as usual. You have the delta plus, delta minus, so the nucleophile attacks here, breaks the pi bond, and gives you the tetrahedral intermediate. And if you remember, with aldehydes and ketones, those tetrahedral intermediates will often end up being the final product. But when you have acyl derivatives, these have a leaving group on the carbon, which can leave. And I didn't show the key arrow there to show that bond breaking, because this OET is not a great leaving group, but it's good enough, and probably as it's leaving, it's tending to pick off this proton anyway. So we get a nucleophile elimination step, reforming the carbon-oxygen double bond, and we get an acid-base step at the end to give us the final product. So there's a typical example of an acyl substitution. Now, if you want a reactive acyl derivative, you usually use an acid chloride or an anhydride. So So there's your acid chloride, hopefully remember that, and anhydrides. Now, if you were just to mix an acid chloride with an alcohol, you will get a reaction happening. But the problem is you generate HCl as a byproduct in that case. So you would either turn your nucleophile into an anion, in which case now the leaving group is just Cl minus. But often the most convenient way is just to run the reaction in the presence of a base. One that I've used is triethylamine, which is, or triethylamine if you're British, and pyridine, an aromatic ring containing a nitrogen, And there's another one which I want to cover. And that's called Dmap. And, oh, sorry. The NH2 compound is used as a drug for multiple sclerosis, which was one of our posters recently. But that's not what I'm talking about here. It's the dimethylamino-pyridine. Now, all of these will work just as bases, just using the lone pair of the nitrogen, and leaving you a product which is a protonated amine byproduct. But the Dmap actually catalyzes the reaction. The pyridine probably does as well, but Dmap is being found to be particularly effective for this. So let me show you how that works. Now, this is an example of the use of Dmap, in this case for an acetylation of an alcohol. I picked just a simple alcohol, ethanol. And acetic anhydride, which is less reactive than an acid chloride, but it's a lot more convenient to work with than acetyl chloride usually. And here's the Dmap. And what the Dmap does, in effect, is it does a substitution via the usual mechanism. Here's the nucleophile addition. Tetrahedral intermediate. Then a nucleophile elimination. Only now what we've got is not a neutral group. We actually have a positively charged group. Now that's actually a much better leaving group than the acetate was. Apparently, anyway, according to the book, reactions of acetic anhydride go 10,000 times faster with Dmap present compared to without it. So clearly it's having a big role in promoting this reaction. The ethanol can attack this activated version of the acetyl group now and react very easily to form a new tetrahedral intermediate. So another nucleophile addition, giving us this tetrahedral intermediate here, which can then now push out the Dmap group, nucleophile eliminations, and give us the protonated form of the ester. And now we've got a strong base present, and this is a fairly strong acid, so this will do an acid base at the end and give us the ester. Now, a couple of features I want to show about Dmap. One is it's got these two nitrogens, and these two nitrogens actually talk to each other, meaning they're electronically connected to one another. So you've kind of got the power of two nitrogens, which makes this a little more basic. Pyridine is not really a strong base. The dimethylamino group makes this a lot more basic and a lot more powerful at adding like this. So what happens if this nitrogen reacts, and this is probably the more basic nitrogen, it can act, it could just act directly, but it can also act through the ring system like that. And that's what it often does. And it gives this protonated form like this, and then that can carry on through all the way. Now I've also shown it doing the same thing over here, where it's doing the acid-base reaction. I'm showing this reaction pushing the arrows and giving us the protonated form here. Now you may look at that quite reasonably and say, but hang on, aren't we destroying the aromatic ring system? Pyridine is aromatic, it's genuinely aromatic, 6 pi electrons. This lone pair is actually outside the ring, it doesn't take part in the 6 pi electron system. So it's 6 pi electrons, not 8. And so this is a truly aromatic system, and we've kind of destroyed that, so it looks like. But in fact, as I've shown here, the protonated form of Dmap, and that also applies, by the way, to the way the Dmap appears in here. There are resonance forms that can share that plus charge between the nitrogens. So you can see here, oh, sorry, there's only one plus charge on here. So that's today's deliberate mistake in the lecture notes. So this lone pair can also share in stabilizing the charge. So the plus charge is shared between the two nitrogens, and that's what I meant by them talking to one another. And you can see in this resonance form we have a fully aromatic system. Remember what I said, the lone pair is not involved in the aromatic system. So protonated pyridine is still aromatic. So this is a fully aromatic system. So if this is fully aromatic, this must be as well. The system as a whole is fully aromatic. So remember, resonance forms don't always give you the whole truth. You can be misled by them. So the upshot of this is that Dmap is quite a good base and stronger than a simple amine or a simple pyridine, and it will catalyze acylation reactions like this very effectively. So the overall reaction then that we've done is so there's our overall reaction, which is an alcohol plus an acid anhydride giving an ester. And a similar mechanism will apply to a lot of acylation reactions involving Dmap. Okay, there's another activating agent that people use, which is used for the Yamaguchi esterification. So I'll cover that next.